I'm Bill Bain from ScaleOut Software, and I'm going to talk about in-memory computing and how it's used for operational intelligence to solve business challenges, and give you a little bit about our evolution as a company in this area. You know, I didn't think that would work. Yeah, it works. Okay. So I'm the founder and CEO of ScaleOut Software. I've worked in parallel computing my whole life, and well, not my whole life, since graduate school. And we started this company in 2003, been in the market since 2005. We have about 450 customers running on about 12,000 servers. And we have a major airline, major news company, major shopping site. So over the years, we've learned a lot about how in-memory computing technology can be applied to a variety of applications. We developed a technology called an in-memory data grid, which was referred to this morning in the keynote, and it solves two problems. First, it scales application performance by hosting fast-changing data in memory and scaling that across a cluster of servers. And secondarily, it's used to analyze data in memory using data parallel computing techniques. So there's two opportunities for in-memory data grids. One is data storage, and the second is computing. And I'll tell you about some of the evolution in people's thinking as they move from just storage to computing. In-memory data grids, to recap, it's key value store, scalable, transparent, location transparency, high availability. Okay, so you can see that this is a very useful adjunct to an object-oriented program, because fast-changing business logic state can be stored in memory and scaled across a cluster of servers without the application having to worry about how to do that. And so for many years, starting in 2005, we delivered our product primarily for this use case. And there are many applications that you can see for in-memory data grids as a distributed cache. I won't go through them, but you could see some of the use cases that we have encountered. Many of them are in e-commerce. That tends to be a very popular area. And because you're storing things like shopping carts and session state. So in fact, when I started the company, the first thing I did was go talk to Amazon and say, how do you store shopping carts? And I won't go through that story now. But that's when I realized you need an in-memory data grid to really solve that problem. That was a long time ago, before they grew so large. So the next step then is to say, okay, well, how do I get at the data, not just with a key value access, but with query? Because we find that most customers, when they come from relational databases and they say, oh, okay, the database is too slow, it's a bottleneck, I got to move data into memory, and I want the scalable throughput, but I want to query it the way I would query a database, and they immediately run into performance issues. And the problem is that a parallel query has to access all of the servers of the grid, because you're saying, give me all of the objects that match some value for a set of properties or for tags or other ways of describing the data. And this mechanism is provided because customers expect it, except the problem is it takes order in time on end servers. And if you have as many clients as servers, then, and they're continuously producing queries, then you're really generating order in squared overhead for the network. And what you find is that you're quickly saturating the network, and the query response times are going to get slower. And so it's very obvious that what you really want to do is move computation into the grid. However, many people, when they encounter data parallel computing, how do I do this in the grid instead of pulling the data out and doing it in my own compute cluster, it's a little bit intimidating. So we created a mechanism called filter methods, which is a bridge towards data parallel computing. We did this for a customer who wanted to query data, but the querying by property wasn't sufficient. So we said, okay, well, why don't you create a method, and then when you query the grid, and this shows a C# version of this as an extension method, then we'll just run, when you select objects, then in the grid we'll run your method, and we'll let you examine the object and make a decision, yes or no, you want to pull this object out of the grid for reading. And so that way you can do some elaborate algorithm in the grid for the purposes of selecting it for query. And as you can see, the next step after that is, well, why don't we just do the entire computation? Let's not just select the object, let's just perform the entire computation in the grid and return whatever result the computation would produce. So you can see how this is a bridge to data parallel computing. And that has been quite successful. So when you use computing techniques in the grid, you're using the grid for more than just data storage. And the power of that is you're already devoting a set of servers, a cluster, towards implementing an in-memory data grid that's hosting data in memory and distributing across those servers. So now you have both storage, in-memory storage, and you have CPU power, not to mention networking sufficient to support all of that. And so you can now think about doing computation in the grid itself and leverage the ability of the grid to actually analyze the data as it's changing. So if you heard Abe's talk this morning about HTAP architectures, being able to do analytics at the same time you're doing transaction processing, that's a term from Gartner, HTAP. The grid is a really good platform for that because it's integrating both data storage and computational capability in the same grid. And what this gives you is the ability to get very fast feedback on changes in the data. So if the data is representing telemetry from medical devices, you can find patterns and trends and generate an alert very, very quickly because of the fact that you're computing where the data lives and not moving the data out and doing batch processing offline to figure out what the patterns and trends are. So the potential for this is extraordinary. Here are some of the applications that you could consider for doing in-memory computing with data parallel techniques. And we'll talk about several of these, but just to sort of highlight them: e-commerce, providing recommendations; healthcare, doing patient monitoring; IoT, doing predictive analytics; fraud detection for wire transfers. That's a case we saw with a customer. And many other examples. Airline reservations, so matching up customers' airline flyers with their reservations and then with the tracking of their bags, that sort of thing, and being able to know everything you need to know about a passenger so that passenger could be rerouted quickly, bags could be rerouted, and you can quickly respond to changes in weather or aircraft availability. So when you think about operational intelligence, this is a term we saw several years ago when we were first talking about this, is a way of describing the value, the benefit. The benefit is that you can operationally know more about what your data is doing as it changes. And that can be differentiated from traditional business intelligence, Spark, Hadoop, and other offline batch techniques because of the fact that you're dealing with live data sets. They're smaller, but they're live, and they're stored in memory, and you're getting responses within seconds or less than a second. And so this is really good for tracking live data. And the opportunity is that you've reduced the time to when you can take action from offline batch processing so that now you can take action sooner and you have more opportunities that can be captured that otherwise would be missed. And that's the power of operational intelligence, capturing opportunities before the moment is lost. So this is a technique for data parallel computing, one that we implemented. I came out of the supercomputing community prior to starting this company, and a very standard technique is to do a data parallel evaluation of data that's hosted on a cluster of servers and then merge the results. And people often like to use a binary merge because it can be done in logarithmic time and reduce the total time for a distributed merge. So that's this technique. We call it parallel method invocation. And it's what we've done here with the in-memory data grid is adopt it to the object-oriented storage model. So because a grid, remember, it's a key value store, but it's an object-oriented view of data, you can now think about doing object-oriented data parallel computation. In particular, you define class methods for analyzing the data. So if you're storing many instances of a class, like these are cars, car objects, and you want to apply an analysis to a car object, you can do that in parallel with the grid, and it automatically will ship the code out, run it in parallel, and then you can talk about having another method which takes the results, which is a different class, right, and then do a binary merge of the results and return a result object back to the client. Now, interestingly, this can be used to build other data parallel algorithms, for example, the very popular Mapreduce. And Mapreduce can be run as two phases of PMI. And in fact, we've implemented it. We have Mapreduce in C# and Java that's implemented as two phases of parallel method invocation, or PMI. I'll use that term PMI in this talk. And so it's just a building block to other techniques, but it has some really nice advantages. First, it's very simple. This implementation is object-oriented. Third, it's taking full advantage of the servers and cores, and the code is automatically being moved into the grid. And the last benefit is the results. You get one combined result. With Mapreduce, you get a set of results, because that's what the Mapreduce algorithm is generating. But it's many times very convenient to get one result so that you don't have to go collect all the results and orchestrate that work. So here's an example of using PMI in a financial application that we saw back in 2007 or 8. We first saw this stock backtesting. So you take a stock and look at its price history over the last few days, weeks, months, years. And then what you want to do is take a portfolio of those stocks and then take a trading strategy and apply it historically to see how well it performed historically, and then by doing so you can predict whether or not to use it moving forward with that stock. So this is what Cleve Moeller, the creator of MATLAB, calls an embarrassingly parallel application, meaning that there's very little communication. In fact, there's almost zero communication. All of this work can be done in parallel on different stock histories. So what we did was to demonstrate how an in-memory data grid can do this in parallel. We hosted this on Amazon. This was several years ago when the largest instance we could get was 60 gigabytes. Today, you could hold this whole problem in one instance in Amazon. But we distributed this across 75 servers, and we also applied stock price updates while doing the data parallel analysis. And so these curves show different update rates. 10 megabytes per second is the red, and 15 megabytes per second is the per server is the green. So that represented an aggregate update rate of 1.1 gigabytes per second. And we were able to do the backtesting algorithm in 4.1 seconds at that for the green line. And that's really effectively analyzing a terabyte of data at 250 gigabytes per second. That's actually fairly impressive even today. So, and you see near linear scaling. What you want is pure linear scaling. We attribute this to the infrastructure that we probably were spread across multiple, what's the word, backplanes with interconnects. And so the interconnects between the backplanes probably created a little bit of a bottleneck. But in any case, we're getting near linear scaling, which is what you want to see as the problem size grows. And this is called scalable throughput, by the way. This is a term. Cleve Moeller was also the first one to observe this. He worked at Intel supercomputer systems when I was there. And he was the first to observe that what you really want in a clustered system is to scale the throughput by growing the problem size, not by taking a fixed problem size and adding more servers. But you have to scale the workload, and by doing so you get scalable throughput, which is exactly what you intend in the first place. So if you don't move the computation into the grid, you run into this problem that you start moving all the data out of the grid for analysis. This is the problem of using a grid just as a cache. And you can see how this linear throughput scaling, this is the same problem, just tanks completely when you're accessing the data in the grid for use by an external compute cluster. So we simulated that here. This is a different experiment, but it shows the effect of data motion. So the two problems, one is that you're moving data out of the grid, so that's taking time, and it's also bottlenecking the network, because networks are the Achilles heel of today's data parallel systems. Because if you think about it, we have now 8 cores and little laptops, and we have huge amounts of memory that you can get. 32 gig is nothing special anymore. But the 10 gig, or 1 gig is still the standard for networking. It hasn't even moved to 10 gig yet, much less what supercomputers use, which are upwards of 100. So therefore, the network is the bottleneck, and you want to offload the network, and the way to do that is to move the computation into the grid. So the way this a PMI actually runs is the computation runs on all of the servers, taking the objects, applying a query locally instead of globally, and then processing the eval operators, the data parallel method, on all of the objects that are extracted locally, then generating one result object, merging the results locally, creating one result object per server, and then doing a binary merge until we have a final result. And that's how PMI is implemented in an in-memory data grid. Here is another example that we ran across with a hedge fund. So this is a real problem. For a hedge fund that needed operational intelligence. What a hedge fund has is a set of portfolios in different market sectors. For example, high-tech, energy, real estate, and they have a collection of equities they hold in each of those market sectors, and the goal is to balance the short and long positions so that they're hedging, which is their job, right? So for their clients. And so the challenge is that they were doing all of this in a database, and when the market prices would change, it would take them about 15 minutes before they would know whether or not they had to sell or buy a stock or create a, or short a position. And so that was not workable, right? So how does in-memory computing solve this problem? And what's interesting here is what's data parallel computing, this is something I learned many years ago at Intel, is that the essence of data parallel computing is to know the domain on which you want to apply the data parallel algorithm. And when we talk to customers, the first thing we always try to figure out is what's the domain. So domain is just a term for what are the set of objects that we want to process in parallel. And it can be non-obvious. The next example after this will show you how it's non-obvious. This one is fairly obvious. The domain is the set of portfolios. So here's a portfolio, high tech, shows the long and the short positions. Shorting Apple there apparently. I'm not sure why. And so the way this could be implemented, and this is at a time when we only had data parallel computation, we didn't have stream processing yet. What we did was we took a market feed snapshot once a second. So collect all the price changes every second, take that snapshot as a parameter to the PMI, to the parallel method invocation, and do a data parallel operation across all of the portfolios. And then at each portfolio, the data parallel method would examine the long and short positions relative to the stock price changes, apply those price changes, and see what was required to rebalance, and if using a proprietary, highly secret algorithm, which we never got to see, and then to create an alert for a trader if that portfolio needed rebalancing, because at the time they did not want to do automatic rebalancing. They wanted to do manual rebalancing, but they wanted to know about it within seconds. And so this is a data parallel operation that is performed once per second and generates alerts. So we did that we showed them how this would run, created a proof of concept. This is the display we created, the dashboard. And so we had about 2,000 strategies in the grid. And we were able to perform this in this data parallel operation at 350 milliseconds for all of the strategies and refresh the alerts. So you could see the merge object that comes out has a bitmap of all the strategies which show which ones are alerted. And those are highlighted here. And then the trader can just press on a strategy here, just select one, and then look at it and see all of the long and short positions and actually see where it's out of balance and what needs to be changed because of the deviation. So you can see this stock needs to be bought or sold, I don't know what right now, but you can see it's been alerted. So so you can see the data parallel operation examined all the portfolios, collected all the results, and presented alerts which are refreshed once a second for the trader. We showed this at trade shows for a few years, and if you're very interested, we can resurrect this demonstration for you to take a look at. Here's another example where the domain was not obvious at all. We're working with a company that's selling perishable goods in very large volumes. And they had two siloed databases, one for their orders and another for their inventory. And what the problem they had was that people, their online representatives would fill orders for which they couldn't be certain there was enough inventory. And inventory for perishable goods changes very, very rapidly. There's a lot of turnover. And you're also predicting the arrival of inventory that's not there yet. Very complicated business. So the problem they had was they'd fill an order and find out the inventory wasn't going to be there on the day that they needed it, and then they'd have to go back to the customer and give them a gift certificate, and they were losing money. So they wanted to solve this problem. So they did what I would consider the obvious approach, use the grid as a cache, and just we had two databases, so let's create two namespaces, we call them, or collections in the cache, in the grid. I'm using the term grid and cache interchangeably here. So have one for orders, one for inventory by SKU. So that's what they did. And then they had a compute cluster, and then they would run a reconciliation algorithm. And by the way, the reconciliation, just as the hedge fund had a very proprietary algorithm, they have a very proprietary algorithm for reconciliation. And so this algorithm would run on the compute cluster, one for every SKU. They only ran it once per night, like 2 in the morning, and it would take more than an hour to run. I think a lot more than 1 hour, actually. And what it would do is do a query of all the orders for that SKU, and then query all the inventory changes for that SKU, and then reconcile them, and then produce alerts if there was a mismatch. Of course, it's many, many hours later than the order was taken, so that didn't really solve the problem. So my colleague here, Oleg Schmidtov here, and I went and visited the customer and scratched our heads to try to figure out what's the solution to this. So anybody want to hazard a guess at how you might actually reorganize this to eliminate the query? Okay, but I thought I'd throw that out. So what we came up with is, look, you got to get rid of the queries. That's the first thing. And the way you do that is change the domain. The domain is not orders and inventory, it's SKUs. So if you just reorganize the objects by SKU, then orders can update the SKU object, inventory changes. So you have two collections, if you will, inside of a SKU object, the set of orders, the set of inventory changes. Now you have all the information pre-joined in a SKU object for doing a data parallel computation. Now you can either read those objects one by one and perform this in a compute cluster, or you can just leave them in the grid and do a data parallel computation directly in the grid. And when you do the data parallel analysis in the grid, the data doesn't move. So you don't have to read all that data out of the grid every night. In fact, you can do it in real time. And it takes well under a minute. I don't remember exactly how long it takes, but it was just several seconds to do this for the entire set of SKUs. There were like 50,000 SKUs. And by doing this, you can examine all the SKUs in parallel using the grid servers and generate alerts which you can feed out to the analyst or whomever you need to take care of it. So now you can do real-time reconciliation, and in fact, you can avoid filling orders that you shouldn't be filling because the inventory won't be there. So you can imagine ways you could evolve this beyond this so that actually when an order is being placed, it'll just go off and examine just that SKU and see, is it going to be possible? So in any case, this shows you another real-world application we ran into for solving the problem of how do you use a grid for in-memory computing to give you operational intelligence. So, and I was so worried I didn't have enough slides. So this is a problem we ran into with a financial services company that had a column-oriented data, and they wanted to perform operations on these columns. And so they said, just tell us where they are in the cache, and we'll go find them and go, I want to know what server the column is on. And we said, no, that's not the right way to solve it, because once we reload balance our grid, you won't know where they are anymore. So what we did is created essentially stored procedures. So this is another, it turns out to be another form of data parallel computation. We call it single method invocation. And what it says is run a method on a specific object, not on a collection of objects, and do that with the fastest possible the lowest latency by going directly to the server, running it, and then returning results without any store and forward through the grid. So do this as fast as possible, but then let us run our highly proprietary column-oriented computation on the objects in the grid. And now we'll do this in parallel for many different columns, and then we'll collect the results, the customer will, and then do its algorithm in the client for summing up the results, whatever it's going to do. We created a new mechanism called single method invocation. So instead of doing data parallel across many objects with one method, we can run a different method on an individual object. So it's like a stored procedure. So that turns out to have been very successful, and it evolved into stream processing, which I'll explain in a minute. So the way we do this is we simply run, this is like I thought I'd just sort of go from examples to architecture and back and forth here. So what's happening is we're running a process on every grid server. These are the grid servers, a separate process that's hosting a language-specific runtime. And that's where this computation, whether it's PMI or SMI, is being executed. And by doing this, you see, we can ship code directly to the worker. All the communication is local. It doesn't go across the network. And lastly, we're protecting the grid service from errors in the application, because those errors won't bring down the grid service. So the value you get from this is that you can now scale computation in any given language that you want. We can ship code out to the grid automatically, and you can perform either SMI or PMI without having to worry about affecting the grid service. Now, if you think about technologies like Redis, have you guys familiar with Redis? So they run Lua but they run Lua in the grid service. And so if you have a mistake or you have a loop, then you can bring down the grid service. So I gave a talk on this topic 2 years ago at IMCS in California, if that's interesting to you. There's more detail here, but I'm going to skip it in the interest of time and talk about another example we ran into. We talked to a cable company, and the problem they had was they wanted to look at what their cable customers were doing by getting telemetry from the set-top boxes. And they wanted to then upsell them first of all, they wanted to filter the telemetry of the channel changes that the customers were making to see what are they doing. They want to try to analyze that, again, using a proprietary algorithm, and then feed that to a recommendation engine to upsell them. At the same time, they wanted to look at what all of the customers are doing at the same time and get aggregate statistics so they would know, for example, what are the most popular programs in a given area, like a zip code. So they were solving two problems. One is, how do I handle all this telemetry coming in, and then how do I analyze it all in parallel? Well, the challenge for that is was very difficult. It took 6 hours alone to correlate, cleanse, and enrich the incoming events. And the reason is because the data comes in from the set-top boxes uncorrelated, and it has to be pushed onto disk, and then offline recorrelated. Correlation of incoming streaming events turns out to be a big roadblock to doing this fast for operational intelligence. Not to mention that there's no way to do aggregate statistics on this data. They had just no mechanism for it. So the solution is to create objects in the grid which represent the set-top boxes. And so every object corresponds to a unique customer. And then to send the telemetry from a given set-top box to its object in the grid. And we did that with SMI, single method invocation. And then at the same time, we could examine all of the set-top boxes in parallel with PMI while those boxes while the objects were changing. So this is interesting. You have live data that's changing. It's churning as the telemetry is coming in. But at the same time, you can do a data parallel computation and understand instantaneously what's going on an aggregate basis by doing the PMI. So you're doing two things at once. And so, when we analyzed an incoming event, we can then forward that to their internal recommendation engine for them to upsell their customer. So I told them, I said, I think we could do it in, in under 5 seconds to get the result out to the recommendation engine. They just wanted it before the customer got bored or fell asleep or walked away. And I think we could do this telemetry in the aggregate statistics in under 10 seconds. And they said, well, we have talking to another cache vendor, and we have a cache in there, and we think you can't do it in faster than 12 minutes, from 6 hours to 12 minutes. So by applying data parallel techniques I just described, we created a proof of concept demonstration for them, and we showed that we could actually enrich the information in under a second, and we could do aggregate statistics in 10 seconds. We ran this on 20 servers in Amazon just to demonstrate it to them. And we were able to hit their rate of, I didn't mention that in the previous slide, but the workload was 10 million set-top boxes with 25,000 events per second. And so their goal was, can you do 25,000 events per second? So we demonstrated over 30,000. This meter went back and forth. And then the aggregate statistics are shown in 2 places. So you can find the top 20 programs by zip code here, or just click on a zip code and this was live data from San Diego that we happen to have a cable TV feed from San Diego. And you can see what is the most popular program in the last 10 seconds. And so it just shows that you could use these techniques of single method invocation and parallel method invocation together to achieve this result of operational intelligence. And so that's that story. There's more to that story, but we'll move on. What we learned from that experiment is that SMI is great for method evaluation, like the financial services application, the column-oriented data. But for handling events like this, it's a bit heavyweight. So we added a new mechanism, which is a very lightweight SMI, and we decided to use the reactive extensions library to implement that. And so the reactive extensions library just streamlines this process of handling events so that we can now handle events at a much faster rate with lower latency. And so the first application for that we ran into, this is another customer, this is a financial services customer, and their challenge was they wanted to query stock data So what they wanted to be able to do is take, for any given stock in the market, look at today's prices and yesterday's prices instantaneously, and then they wanted to apply things like changing the currency in real time so they could tell you right away what this stock was worth in a given currency. So we wanted to provide, again, proprietary operations on that data. So the way they were currently solving it is to have a replicated database. They had 12 plus replicated databases. And so when a stock price change would come in, they would apply them to all of the databases. The two problems remain, though, is that these databases are now not coherent. So depending on which one you hit, you might or might not get the latest price. And second is that they were having to move this data out of the cluster, out of the database. They're having to do database access every time they wanted to access any of the stock price information, and that's high latency, with a compute cluster. So they also had to schedule, they had to write an application-based scheduling algorithm for their compute cluster. So it's complicated and a little bit difficult to use. So the solution we came up with is keep at least a pair of objects for every stock price. Well, one represents yesterday's prices, one represents today's, and then you could chop that up more. And then what happens is use stream processing with ReactiveX to update today's stock prices, so you can do that with very low latency. And then let the clients just query a given pair of objects from the grid. They don't do a query, they just do a key value read, which is a linear time, order one time, so it's very, very fast. And then rely on the client cache in the client, which is part of the grid, to host the most recently accessed objects. So you're getting the benefit of stream processing and fast data lookup from the grid. And so there's actually more to this than meets the eye. In particular, you want to always implement a special read mode such that when an update comes in and invalidates today's stock object because of an update, the client cache does not suffer a latency hit to have to reread all that data in the client execution path. You just do that asynchronously. And that was an innovation we made to keep the latency as fast as possible. I'm not sure about a demo. Okay, so the next step then is to recognize that, gee, the grid is really useful for stream processing, and there are many applications of it. Now, you might have heard Abe mention the digital twin model this morning in the keynote. Well, the digital twin model comes from a guy named Michael Greaves at the University of Michigan, who created it for the use that we saw this morning, which is to help design large, complex systems with components that are digitized. However, in discussions we had with Gartner, we learned that this model could be very nicely applied to stream processing. In particular, this new area of stream processing called stateful stream processing. And in stateful stream processing, you want to maintain as much knowledge about the data sources as you can, because if you just look at streams of data without regard to the context in which that data is created. So for example, if it's a machine tool and you want to look at telemetry about temperature and you want to decide predict whether the machine tool is going to overheat and fail, you have to know a lot about that machine tool, what it's been used for, what its workload is, what its load factor is, what its history of temperature excursions is. So there's context you need. In every application you can think of, context is valuable. It's state, and that's called stateful stream processing. The problem is most stream processing platforms like Apache Flink don't provide any software architecture for hosting context. But it turns out an in-memory data grid is really very well suited for it because it has collections of objects in the grid. And each object can represent a digital twin of a physical data source. So as telemetry comes in from windmills in a large windmill farm, every object can represent a different windmill and have information about the history of that windmill and its current status and when it was last maintained. And so with the digital twin model, you now can organize telemetry that comes in and solve this problem that we saw before with the cable application, namely correlation, because the grid can automatically correlate events because it's going to deliver them to a given object in the grid. So correlation, you get it for free with the grid because you just send the events to a particular object which represents the data source. It has other benefits. One is that because it's object-oriented, you can encapsulate your favorite analysis algorithm. Like you could have a machine learning algorithm or a rules engine that you bury inside of that object. And so when an event comes in, the reactive extensions event handler can run your favorite algorithm that's domain specific. And in fact, that gives rise to, just to give you sort of like one of the punchlines of one of the learnings of all of this, is that the real challenge for in-memory computing is not all of this architecture and what is data parallel computing. It's actually, what is the domain-specific algorithm that I need to run? The question we always get is, okay, great, you've got a great platform, but now tell me how to do predictive analytics for my cheese boiler. And we go, well, we don't know how to do that because we don't know about cheese boilers. That was a real problem we ran into. A large cheese company that said, okay, we'll send you all this telemetry. Now just tell us when the boiler is going to fail. We said, well, we actually don't know about your domain. So that's the real challenge is, what is the application you actually want to run when you get the events? But this infrastructure gives you a big step forward in organizing the orchestration of the events and the running of the analysis. In addition, it allows you to have a natural domain. Here's the domain again. For data parallel analysis. The digital twins themselves are the domain on which you can collect aggregate statistics and then report them or even better, feed them back into the system. So there are many applications for this. I'm going to skip these and just go to the last one in the interest of time. This is like a rental car fleet or a truck fleet. You can imagine you'd have digital twins there. This is a talk I'm going to give later today about heart rate monitoring for runners. And so you can imagine how you could get telemetry there and feed it back and so forth. We won't talk about that, but just to give you an idea of some of the applications. But the last one I'll talk about is e-commerce recommendations. We've spent some time thinking about this. And the reason we've thought about this one is because it's easy to understand the algorithms relative to, say, medical monitoring or cheese boilers, right? So the goal here is you receive click streams from shoppers and you want to give immediate recommendations. Now, people do that. There's some big companies doing that. But they typically do it with techniques that aren't taking into account the click stream. They're taking into account their knowledge of the shopper and their accumulated knowledge, as evolving knowledge as they click on products. But they don't actually look at the click stream and say, I see what this customer is looking for. Let me see if I can pick the right product that matches the attributes they want. So it turns out you have to be able to do this for every customer within 100 milliseconds. And if you're doing this on Amazon, you have to be able to do it for 1 million shoppers at the same time. So it's a big problem, and it has very tight latency constraints. So this is an example of what the output would look like for the customer, a set of real-time recommendations updated with every product click, and you can allow the shopper to select the attributes that are most interesting, so you give the shopper is giving feedback to the real-time system, to the digital twin of the shopper. And also here, I think I have a highlight, you can look at the data parallel feedback because this system can then look at all the shoppers, figure out what are the best-selling products, and then deliver feedback to the shopper so the shopper has collaborative feedback for making decisions about what to buy because people want to buy what other people are buying. So this implementation then is a set of digital twin objects in the grid which represent the shoppers on which analysis is performed for every click and real-time recommendations are provided in addition to doing data parallel analysis for collaborative feedback, which is both delivered back to the shoppers and delivered to the merchandiser so the merchandiser could create promotions based on what shoppers are doing. Interestingly, there are other domains, there are other collections. In particular, you have to get product information and make that available to the digital twin objects. So there's more to it than just implementing the digital twins. And so this is an example of the dashboard you could create that shows the data parallel aggregate statistics, like the top 5 product categories or the top 5 products in a category, and other things, for example, the percentage of carts that have been purchased, so forth. Those are aggregate statistics that merchandisers need to see. So we might have 5 minutes for you. No, we have 5 minutes, actually. So I'm going to do this wrap up, and then Oleg is going to give you a 5-minute demo of how this would look.